All right, so this is 6.3. We're going to talk about vectors. So with vectors, we're going to talk about the magnitude and direction, which we'll get into that because we'll have different formulas for each. And then we'll have an initial point, which is where we start, and a terminal point, which is where we end. So with our vectors, we have direction. They go in a certain direction. So it's going to have a starting point and an ending point. And it's also denoted by this symbol. So it's not like array, but this just shows you that it's vector PQ. So the directed line segment has an initial point and a terminal point. Its magnitude, which is the length, so magnitude is the length, is denoted by these two arrows. This is our symbol for magnitude. And it can be found by using the distance formula. So this we know from the beginning of the year. We talked about the distance formula and in geometry. Two directed line segments that have the same magnitude and direction are equivalent. For example, the directed line segments in figure 6.12 are all equivalent because they have the same direction and the same magnitude, the same length. So the set of all directed line segments that are equivalent to a given directed line segment is a vector in the plane written like this. So this we can denote a vector, but we also denote it by the bold letter. So a bold V is usually what we see, but we'll see vector U, vector V, and vector W like this. So bold letters tell us that we're talking about vectors. So in example 1, it says, show that U and V in the figure below are equivalent. Well, in order for it to be equivalent, we need the same magnitude and the same what? Direction. So magnitude talks about length. And direction, what do you think direction goes with? How can I tell that these two are going in the same direction? Slope. Anybody remember what our distance formula is? All right, so our magnitude, we use the distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. All right, so let's find the length of our first vector, vector v. So I'm going to call this x1, y1, and x2, y2. So we plug it in. It doesn't matter which one's with which, but it will once we start determining the vector, which you'll see, then it'll matter, the terminal versus initial point will matter. So 4 minus 1 squared plus 4 minus 2 squared. So this will be 3 squared plus 2 squared, 9 plus 4, which would be the square root of 13. So the length of vector v is square root 13. Next, let's find the length of vector u. So we're doing the same thing. I'm going to rename my points x1, y1, x2, and y2, and now plug them into the same formula. So 3 minus 0 squared plus 2 minus 0 squared. So that would be 3 squared plus 2 squared. 9 plus 4, which would be the square root of 13. Do they have the same length? Yes. So they have the same length. Now we have to figure out if they have the same slope, if they're going in the same direction. So to find the slope, you can use your slope formula. Do you remember what the slope formula is? Perfect. Look at that. It's like riding a bike. Or how else could I find the slope? Rise over run. We could just count our rise over run. So I'm going up 2 and I'm going to the right 3. So this would be the slope for vector v is 2 over 3. And let's find a slope for vector u. I'm going up 2 and to the right 3. So 2 over 3. So are the two vectors equivalent? Yes, because they have the same magnitude and the same slope, the same direction. So yes, they are equivalent. Right. So because u starts at the initial point starts at 0, 0, my component form for u would be the same thing as this, 3, 2. But if it doesn't, so v doesn't start at 0, 0. So this is when I would have to do terminal minus initial. Here, which one's terminal, which one's initial? Initial is where we start, and terminal is where the arrow is, where you end. So this would be our terminal. Oops, this is our initial, sorry. This is our initial. This one's our terminal because this is where we end. So it's always the first number with the first number. So for my component form, it would be 4 minus 1. And then terminal minus initial for the second value would be 4 minus 2. So my component form here would be 3, 2 with the brackets. So these two are the component form of the vector.
So x2 minus x1 and then y2 minus y1?
Right.
Is that magnitude?
So the directed line segment whose initial point is the origin. What's the origin? 0, 0. Is often the most convenient representative of the set of equivalent directed line segments. This representative of the vector v is in standard position. So standard position is when the initial point is at the origin. So if we go back to the last page, was one of our vectors initial point at the origin? Which one? Vector u. So that would be in standard position. So a vector whose initial point is at the origin can be uniquely represented by coordinates of its terminal point, v1, v2. So that's the terminal point. So if we go back to the last slide, I had a vector started at the origin and ended here, let's say. What was the point? 3, 2? On the last one for vector u? So this vector, the point, this would be our v1 and this would be our v2. So we would name this vector. Vectors are named with these brackets. So talking about the last example for vector u, we would name it as 3, 2 with the brackets. Because when we have vectors, we name it with the brackets. And the reason why we copy the same exact ones that we were given is because it starts at the origin. But I'll show you how we would find a vector if it doesn't start at the origin. So component form of vector. The coordinates v1 and v2 are the components of v. If both the initial point and the terminal point lie at the origin, then the vector is a 0 vector denoted by 0, 0. So that's if the terminal and initial are at the origin. Now, if we were given a line segment and we had to find the component form of that, and if it didn't start at the origin, what we would do is take the terminal minus the initial. So here it gives it to us as Q1 minus P1 and Q2 minus P2. So this is pretty much just saying it is the terminal minus initial.
Wait, so it's defined what?
So just remember, it is always terminal minus initial.
The formula that says is like V equals Q minus P, like that's because he's being as like the distance formula kind of?
Right, so here we have a formula for the magnitude, which is our distance formula, but it also has a shortcut to it when we're given the component form. So if I had my component form of my vector, I could easily find the magnitude just by squaring the first term plus the square of the second and take the square root. So this is like the shortcut of it, but you could do it the same way doing the distance formula. But you would already need component form to then use the shortcut. All right, let's look at example 2. So we have to find the component form and the magnitude of vector v represented by the directed line segment that has the initial point 4, -7 and terminal point -1, 5. So first we're going to find component form. How do we find component form? Terminal minus initial. So we take our terminal point. The first number goes with the first number, so the x goes with the x. So it would be -1 minus 4. Terminal minus initial. And then comma, 5 minus -7. Have a good weekend. So it's -1 minus 4. -5 and 5 minus -7. 12, because it's turning to 5 plus 7. So this would be our component form. With your component form, make sure you put the little brackets. Don't forget. You'll get points taken off. Yeah, one vector. This is vector v that we're talking about. All right, next it asks us for the magnitude. So the magnitude, we would name it as the magnitude of v, so with the double bars here. So with our magnitude, once we have component form, we can take the square root of the first term squared, so -5 squared plus the second term squared, 12 squared. So this would be the square root of 25 plus 144. So the square root of 169, which is 13. So our magnitude is 13.
Like let's say if we were to write our final answer with that.
You got to put it somewhere so I know that that 13 is talking about the magnitude. So we have vector operations. We can add vectors together and we can multiply vectors by a scalar. So when we multiply vectors by a scalar, it's just like a coefficient to our vector, but it changes the length. So if I multiplied my vector v, this vector here, by 1/2, the length would change by 1/2. So if we multiplied vector v by 2, it would double in size. If we multiplied our vector by a negative, the terminal point becomes the initial becomes the terminal. So it just changes direction. So our vector can change in size and direction. Same thing. It's flipping the direction and being multiplied by 2/3. So it's the length and a half. All right, so we can add two vectors together. I'll show you mathematically on the next slide how we would add and how we multiply by a scalar, but graphically, how we add vectors together is we take the first vector. So we're adding u plus v. So we take vector u and then take vector v and just move vector v, the initial point, on top of the terminal point of vector u. So if you have notability, you can highlight this, drag it on top. I can't show you, but you would just take this same shape, move it there. So this is vector v. Connect it. You're just putting one on top of the other. And your vector u plus v would now have the initial point of vector u and the terminal point of vector v. So it would be this line. So here it shows you how to add your vectors and multiply by a scalar. So if I was adding vector u plus vector v, we add the first two numbers together. That would become your new first number here. And then add the second two numbers. So the first number gets added to the first, the second number gets added to the second. That's your new vector. When we multiply our vector by a scalar, so if I had k is my scalar here, but it could be any number. It could be 1/2, it could be 5. We distribute that number to both numbers on the inside. So it gets multiplied to the first number and the second. Here we also have the negative of a vector, so it's negative vector v. The negative just gets distributed to both numbers on the inside, so this is important to know. And then when you're subtracting vectors, it's the same thing. First number minus the first number of the other vector. Second number minus the second number of the other vector. So the first numbers go together, second numbers go together. We just have to do whatever it says. If it says to add it, we add it. If it says subtract, we subtract. This one again is showing you what it looks like to subtract vectors. We'll come back to this. All right, so here we have our vector operations. So for A, I'm multiplying vector v by a scalar. So this is 2 times -2 and 5. So when we multiply by a scalar, I have to distribute the 2 to both numbers. So what would my new vector be? -4, 10. Let's look at B. So for B, I'm subtracting w minus v. So it's 3, 4 minus vector v, which is -2, 5. So just be careful. The first number goes with the first number, second number goes with the second. So this would be 3 minus -2, which would be what? 5, thank you, because it turns to a plus. And then 4 minus 5, which would be -1. So this would be our vector. C. So vector v would be -2, 5, plus 2 times vector w, 3, 4. What do you think I have to do first here? Multiply, just like our order of operations in normal algebra. We got to multiply first. So this turns into 6, 8. Now which two numbers would I add together? -2 and 6, which would be? And 5 plus 8? 13. If this was for 13 on the graph, it would be here, that. But if it was vector for 13, it would be that. Are those the same thing?
They fall in the same place.
No. One's a point, one's a vector. Not the same. The last slide just talks about properties of vectors. So it's, same kind of that goes with like algebra. The order doesn't matter. You could add vector u, vector v, or switch it. If you add the 0 vector to it, 0 plus a number is still that same number. So multiplying, the order doesn't matter if you multiply the two numbers together or distribute one first. So the order doesn't matter there. Same thing here. You could distribute the c. When you're taking the magnitude, remember double lines mean magnitude. If you had a scalar, you could multiply the scalar to the vector first or multiply the scalar at the end. When adding 3, you could add 2 of them together first. The order doesn't matter. If you have the same vector plus the negative of that vector, it gives you 0. Same thing here. You just distribute the u. 1 times the vectors, the same vector. 0 times the vector is 0. Pretty straightforward.